This lesson's about diffraction of waves. Diffraction refers to the way that waves bend when they pass around obstacles, or also when they pass around the edges of an opening. So here are wavefronts propagating left to right towards this obstacle, and what we'll see when they pass the obstacle is, here's what they don't do. They don't just keep going, creating a completely empty shadow region behind this obstacle. What you'll observe them do instead is that they curve around the obstacle. And so while they might be straight here, they're going to curve here a little bit and then continue to curve and continue to curve into the shadow region like this. So there's a straight portion and then there's a portion that's curving like this into this shadow region over here. And I'm referring to this part in the middle here as the shadow region. Now, whether or not we observe that, or whether it's a subtle enough effect that it looks like they're just still going straight, depends on things that we'll talk about in a moment. You can see the same effect with wavefronts that then pass through a gap. So here we have two obstacles with a gap in between, an opening in between. Let's take a look at this in a simulation. So this is a simulation from PhET. The URL is here at the top, and we've got planar water waves moving from left to right. The bright blue is the crests, the black is the troughs, and they're passing through this opening, and you can see that they're spreading into the shadow region. They're not letting this region and this region be without waves, but rather the waves are spreading out. And we can actually change the amount that they spread out. If I increase the wavelength of the waves more than I did before, so here you can see the crests are farther apart, then now they are actually spreading out more into the shadow region than they were before. And I can have the same effect by decreasing the width of the slit, the opening that they are moving through. So now if we watch that, you'll see that they're spreading out even more. It's more and more circular. So compare what we've got here. Now I will increase the width of the opening, and you see that they're not spreading out quite as much. There's this kind of flat region to the wave in the middle. And similarly, if I go back to the higher frequency, shorter wavelength I had before, you can see that there's this long kind of flat region, and they're not spreading out at quite such an angle, such a big angle into the shadow region. So changing the wavelength and changing the width of the opening can affect how much it spreads out into the shadow region. Now, one way of starting to think about what's happening here is using a principle known as Huygens' principle. Huygens' principle says that we can think of each point on the wavefront as if it were a source for tiny little wavelets that themselves were propagating out at the same speed as the overall wave. So what do I mean by that? I mean that we can think of, if I take this wavefront here, I can think of each point, and I'm not going to draw all of them because there are infinitely many, but I'm just drawing a selection. We can think of each of them as a tiny point source of waves, so circular waves that are propagating out from them. And the second part of Huygens' principle is that if we want to figure out where the wavefront is at any later time, it has to be tangent to all the tiny wavelets. So what do I mean by that? Well, here are the tiny wavelets, and if I draw a tangent to all of them, and imagine that there are infinitely many in between, so infinitely many circles, then the tangent to all of those circles would be a line like this. And it's not here just because I haven't chosen that time. It could be. So this seems like a complicated way of showing that the wave here is just going to propagate forward, giving you these straight line wavefronts. But it becomes helpful when we start to think about what's happening here. So here, just at the edge of leaving the obstacle, imagine now that I have these wavelets emanating from these points. And you can see that the ones that are off to the side here, like this and like this, are still going to create that kind of flat tangent. But this one here, on one side, is unopposed. It doesn't have a neighbor that's going to interfere with it to make a straight line tangent. Same thing over here. While these two at the top are going to create a straight line tangent, the one here down at the bottom has no neighbor, and so it ends up curving the tangent. And so you can see as a result that I end up with this curving, if that keeps going, into the shadow region. And so that's a way of thinking about what's happening here. You've got these unopposed wavelets at the edges that are causing this curvature of the tangent. Now we can see the same kind of thing if we think about the opening here. If I imagine points here, here, and here, and again there are infinitely many, and think about the wavelets that are coming out from them, then in the center they're going to some to give us that straight line. But once again, at the edges, the tangent is going to curve. And so Huygens' principle gives us a way of thinking about why that curving is happening by thinking about these unopposed wavelets that we're getting at the edges of an obstacle. Now, you can also quantify the amount of bending that happens, and we could get more precise about this, but for now we'll say that the angle in radians of diffraction, and what I mean by that is if we measure from the center out towards the edge, this angle here, that angle there, is roughly equal to the wavelength of the waves divided by either the width of the opening or the length of the obstacle. So I'm calling this distance in both cases d. That's the width of the opening or the width of the obstacle. So if we think about this ratio, if the wavelength is small relative to the obstacle or the opening, then theta is going to be small, and we're not going to see much diffraction into the shadow region. And so the shadow region is going to stay relatively dark. Whereas if the wavelength is large relative to the obstacle or the opening, then we're going to see a big theta, a lot of diffraction. And that actually explains a number of phenomena. First of all, you can hear around obstacles, but you can't see around obstacles. So that's because the wavelength of sound waves, if we think about sound waves have a large wavelength relative to the obstacles, let's say the width of a doorway that they are diffracting around, whereas light has very tiny wavelength relative to the obstacles, and therefore theta here is very, very small. And so we see very little diffraction of the light waves through a doorway, for example, but we see a lot of diffraction of the sound waves. And because the sound waves are diffracting, they can reach your ear if you are over here, let's say, but the light waves are not going to reach your eye if you are in the shadow region. Similarly, you know that you can't see very, very tiny objects like atoms, for example, using a light microscope. And that's the same thing again. Although the wavelength of light is very small relative to that of sound, it's big relative to tiny objects like atoms. And so in that case, again, you have a large wavelength relative to the obstacle. And so you're going to see a lot of bending of the waves in behind the obstacle. And if you think about this continuing, and these bending in further and further, at a certain point they're going to collapse together. And if your eye was looking at this and you were seeing this wave coming towards you, this is not giving you any information or evidence that this ever existed over here. And so you can't tell using wavelengths that are too long that there was an obstacle here at all. In other words, you can't see it. However, if you had a smaller wavelength, then you would not get as much bending into the shadow region, and by seeing that shadow, you'd be able to tell that the obstacle was in fact there. So that's an introduction to diffraction and some of the phenomena that it gives rise to.